So this is the final meeting of the seminar for the year, and today I will give a talk, and I will be talking about homotopy categories of model categories and some extra structures that arise from them being homotopy categories. Okay. So. Okay, so let's start from something that was mostly discussed by Misha. So first of all, well, I don't know, maybe not in these exact words, but will be very close to what Misha covered in his series of talks. So assume that we have a model category, and then we of course have a functor from category of co-simplicial objects and the category of simplicial objects into this model category. Just takes an object and evaluates it at 0. It can be seen that this functor is both right and left within functor. It's quite evident if we consider the reading model structure on both of these categories, since these are clearly reading categories. Okay, so since this is both right and left within functor, we have, of course, left and right adjoint in both cases. So we will denote by L upper bullet and R upper bullet corresponding left and right adjoint for co-simplicial objects, and by left lower bullet and R lower bullet the same thing for simplicial objects. So after a bit of thinking, we arrive to this formula, so we can compute this left and right and co-simplicial objects just by taking the n+1 coproduct of n+1 copies of A at degree n, and for Rn we just take the object A. And so we have a canonical map from L dot to R dot, which is just given by folding these copies of A into one copy. And absolutely similarly, we have and the same thing for simplicial objects. Here we just map via the diagonal. Okay, so we have these 4 functors, and this allows us to define the notion of a co-simplicial frame for an object in a model category. So assume that we have an object A. Then we want to, in a sense, define a resolution of this object, co-simplicial resolution, and it works like this. So we take LA, we take RA, we have this canonical map, and we factorize it into cofibration followed by weak equivalence. So what we get is something that we call co-simplicial frame. If additionally in dimension 0 we have this, so here in dimension 0 we have, of course, copies of A. So this is L of A in dimension 0 and R of A in dimension 0. And here we have the identity. And we also require that for A upper star, we also should have an object A and some isomorphisms. So that's a co-simplicial frame on an object. now we can define a global notion of a left framing on a model category. So we say that the left framing is a functor from this model category into its category of concentration objects. A to
Sorry,
A upper star. Yeah, sure.
A upper star is a concentration set?
It's a concentration object.
It's okay.
Yeah. So yeah, as I said, the idea of a frame is a sort of resolution for an object, and in fact, maybe if we'll look at this a bit closer, we will see that actually, since for quasi-simplicial objects, it's just n+1 copies, coproduct of n+1 copies of A that is mapped by a folding map into A. Then, for example, if we take this quasi-simplicial frame and take it in degree 1, then we will get something that is in fact a cylinder object. Cylinder object of A. So we basically you can in a sense think that we create this maybe, I don't know, a telescope which resolves our object A, and that's the meaning of quasi-simplicial frame on an object. So
okay, and result depends on the degree of L and R. Yeah.
Sure.
Okay.
No. I mean that in dimension 0, this factorization just amounts to saying that we factorize the folding map, and as we will well know, the factorization of the folding map is in fact a cylinder of an object A. So that's just the reason why in degree 1 we have the cylinder, and in higher degrees we sort of have higher cylinders, and they all together assemble in something that can be thought of as a telescope, I guess. Okay,
thank you.
Yeah, sure. Great question. Thank you so much for asking it. So, yeah, okay. So a left framing is a functor from the model category to the category of quasi-simplicial objects, such that in degree 0 we still have an isomorphism. So it's still somehow a resolution. And we additionally require that if the object A was cofibrant, then its A upper star is a quasi-simplicial frame for this object. Okay. So similarly, we have a notion of right framing or right of simplicial frame and right framing. So we should here we should just replace L upper dot with L lower dot, do the same thing for R, and require that we have a factorization where here we have an equivalence and here we have a fibration. And then we will get a notion of a simplicial frame and respectively right framing. So a framing on model category C is a left framing plus right framing. So spelling it out, we have just two functors from C. One goes to quasi-simplicial objects and another goes to simplicial objects. And A upper star is a co-simplicial frame for cofibrotase, and A lower star is a simplicial frame for fibrontase. So that's the idea. Okay, and actually, it turns out that we can define a canonical framing, which is canonical with respect to the functorial factorization. So if we have a morphism of model categories which preserves functorial factorizations, then these canonical framings are preserved. So, of course, it is easier to see that the notion of left framing and right framing are dual. So to construct both left and right framing, it is sufficient to construct just a left framing, and then you can apply the same construction to the dual category. So to prove this theorem that we have this canonical framings, we just construct the left framing, and we do this using an iterative construction. So we start from the object A, and then we define A0n as an object that appears in the functorial factorization of a map from the Lechin object of A0 to the matching object of A0. Of course, it's somewhat nonsensical because A0 is not yet defined. So actually what we mean by a Lechin object of A0 is this co-product, and the matching object is this product. Or if you want, you can just think that this thing is taken in a truncated category, and well, then the notion of a Lechin and matching object again makes sense. Okay, so why we were doing this? Well, actually, the idea is that we want to sort of have some kind of sequential structure on our model category. More precisely, using frames, we can define several adjoint functors, which do not give our model category structure of enriched category, but still they are suitably well behaved with respect to homotopies of statistical sets and homotopies in the model category. And in fact, this can be put into a larger context of derived enrichment, but I don't think that I want to cover it today, but I think that it is beautifully explored in, let me recall. So it's derived enrichment. It's chapter 10 of Riedl's categorical homotopy theory. And it's very actually very close to what Misha was doing earlier. So what we get using these framings? Well, first of all, we get this functor which maps simplicial sets into our category, and we have an adjoint functor which maps our model category into simplicial sets. So how does it work? Well, of course, here we have a simplicial object A upper star, and we want to plug in a simplicial set, and we can just given a co-simplicial object and a simplicial set, we can mash them together to obtain an object in our model category. And dually, we have a functor from the opposite category of simplicial sets. So from co-simplicial sets to our model category, which plugs in a simplicial set into this form, since our category of simplicial objects is co-tensored over simplicial sets. So yes, that's right. So if we have a category of simplicial objects, that's co-tensored over simplicial sets. So it means that we can define this home object, which lives in our category C. And similarly, we can define an object which goes from the opposite category of category C into simplicial sets, so just by usual construction. So if we have a simplicial set, we map into the simplicial object. We map from an object in category C into the simplicial object. We get a simplicial set. So we get a pair of adjoint functors. So one of them goes from, so this is the tensor product. One of them goes from the product of this model category C and simplicial sets into the same model category. And another one goes from the product of C open C into simplicial sets. And we have the dual things. And so we have map L and map R, which corresponds to two choices of adjoint functors. And so what this collection of functors actually give us? Well, turns out that these functors, although they may be are not exactly equivalent functors, but they're actually homotopical on a retract, so they're deformable, and that means that we can define total left and right adjoints of these functors, and we have a functor of tensor product from this category. Maybe I should change the variables. Should I? Yeah, I should. So we have this functor and we have this functor. And then we have total derived functors. So for this one, it's the left derived functor. For this one, it's the right derived functor. And as it turns out, these functors of mapping spaces also have right derived functors. They're also deformable, and if we take their total right derived functors, they coincide. And so we have this isomorphic, so we have this chain of isomorphisms between various objects defined using these functors. So basically, that's just the condition that we have the tensor homojunction. So we have this isomorphism by adjunction. Then we have this isomorphism because derived functors of map L and map R coincide. And then we have an isomorphism because I guess we have the tensor homojunction, which comes from the adjointness of tensor product at home. Okay, so we arrive to our first structure, which so we have the structure for homotopy category of arbitrary model category. And this structure is as follows. So we take the homotopy category, and turns out that it is a module over the monoidal category, symmetric monoidal category, which is the homotopy category of simplicial sets with the usual conclude model structure. So what does it mean that it is a module? Well, it means that we have three functors. We have this tensor product, which here is denoted by tensor L, but actually, if we just thinking about abstract modules over monoidal categories, it doesn't really matter. So we have this home, which takes an argument from this monoidal category. And we have, and here is an argument from our category OC. And we have an internal home. So that's the condition that our module is closed. And the interaction between these three functors should be as in this sequence of isomorphisms. So that's the first kind of structure that we can get on a homotopy category of a model category. And well, of course, homotopy category should be complete and co-complete, but that's that is a very primitive structure. So this, of course, is far more interesting than just some completeness conditions.
Sorry, could you repeat? What is what does it mean? Map L and map R.
Oh, okay. So I'm not sure that I gave a very good or clear definition, but basically we have this functor, this bifunctor of tensor product, and map L is they are joined by functor. So, well, yeah, that's
left and right joined to this functor. Yes.
Yes.
Okay.
Mm-hmm. Okay, so yeah, so now let's move on from this construction to to a more functorial point of view on this situation. That means that we have two categories of model categories with morphisms given by Coulomb junctions, and we have a homotopical pseudo two functor from this two category to the two category, which is given by modules over the homotopy category of spaces, with morphisms given by adjunctions which preserve this model structure, module structure. And of course, the same thing works in monoidal settings. So if we replace model categories by monoidal model categories, and if we replace modules with algebras, then we also get such homotopy pseudo-true functor. And more importantly, we can do this thing. Yeah, okay, so we can do this thing in the pointed setting, meaning that we, instead of model categories, we can put here pointed model categories. Here we can consider still equivalent junctions, but the ones which preserve this pointed structure. And here we would get a functor not into modules over homotopy category of spaces, but actually into modules over homotopy category of pointed spaces with the junctions which preserve this module structure. So we can replace simplicial sets with pointed simplicial sets and model categories with pointed model categories, and everything still works. And I guess, once again, it would be better to deal with it using some general machinery of derived enrichment, but due to time constraints, I don't think that I will be able to cover it today. But yeah, that's the idea. And another small digression which I wanted to make is the relation of this construction to simplicial localization. So it is well known that if we have a relative category, meaning that we have a wide subcategory W inside of C, which satisfies 3-for-2 property, then there exists a simplicial category LWC, such that if we take pi0 of this simplicial category, then we get just the usual localization. And this is called simplicial localization, or Dwyer-Kahn localization, or Hammock localization. So the thing is that all this business with framings is a model categorical way to sort of circumvent this, in a sense, logically tedious construction where we have to take this hammocks and define these simplicial sets of morphisms using hammocks, which may lead to some problems with size and stuff like that. And instead, we just directly arrive to homotopy category with an action of the homotopy category of spaces. So it is not quite equivalent because as a result of this, we don't get necessarily a simplicial category, we get a homotopy category with sort of a shadow of a simplicial category. So, of course, if we have pi0 of simplicial category, then this thing becomes at least it becomes tensored over the homotopy category of spaces. Yeah, so this relation is not quite straightforward, but they're certainly related. So in the end, we get the same thing as we would get in the simplicial localization case, but using a completely different method and using a completely different method. I guess that's all I have to say about the relation to simplicial localization.
Sorry,
okay, so yeah.
Sorry, relates. Recall what is a relative?
The relative category. relative category is just a category with a wide subcategory, meaning that it contains all the objects, and the 342 property. So
okay.
yeah. So that's just like a weak version of category of homotopical category. Instead of 642, we require 342. Only 342. Yeah. Okay. So now let's discuss another even more interesting example of extra structure which appears on the homotopy category of model category. And this is the case of pointed model categories. So I'll denote the two categories of them by MC star. And if, so as I said before, if we have a pointed model category, then the homotopy category of this model category is in fact a module over the homotopy category of pointed spaces. And the proof is almost identical, or it follows from general machinery of derived arrangement. So our goal in the remainder of this talk will be to prove that, well, not proof because today there will be very few proofs, but to sort of see how the homotopy category of a pointed model category is pre-triangulated and even triangulated if C is stable. So what is first of all, let me just briefly explain this goal here. So pre-triangulated means that it is triangulated, but a bit weaker. So we know that in triangulated categories, we have sort of these triangles which are invariant under shifts. So if we have a triangle, we apply a shift function, and we get, once again, a distinguished triangle. But here, this is not necessarily the case. So pre-triangulated categories are categories where we have, instead of one kind of distinguished triangles, two kinds of distinguished triangles. So left triangles and right triangles. And left triangles are invariant under positive shifts, so suspensions. And right triangles are invariant under negative shifts, so applying the loop space function. And that's the structure of pre-triangulated category. Of course, I will give the necessary definitions a bit later, but the idea is that we have this sort of weaker triangulated structure on the homotopy category. Okay, so let's talk about suspension and loop functors. So suspension and loop functors are maybe a bit unexpectedly functors which are defined only on homotopy categories of model category, and their definition uses this construction of derived tensor product and derived home. So of course, in a pointed model category, instead of product or tensor product, we have this smash product, and instead of home, we just still have home. So sigma x, the suspension, is defined as the derived smash product of this object with the simplicial set, which represents the circle. So it can be the minimal circle or something homotopy equivalent. As we know, this derived smash product preserves homotopy equivalences in both arguments, as we discussed earlier. And similarly for this derived home space. So using the definition of derived smash product, and the way that well, the minimal model of S1 is constructed in simplicial sets. So that's just the push out of the map from the boundary of one simplex into one simplex. We get that actually the suspension is the cofiber of the following map. Maybe for some reason I did not include the definition of cofiber, which is essential, of course. So the cofiber is just the same thing as a quaternal. So if we have a map from X to Y, then the cofiber is a push out in this diagram. So yeah, using this definition of S1 and the fact that delta D of delta 1, the boundary of delta 1, are just is just a disjoint union of delta 0 and delta 0, and the smash product with delta 0 doesn't do anything. We see that actually we get this Weich product of cofibrant replacement of X with itself, and it is mapped into smash with delta 1, but it can be seen that actually the smash with delta 1 always produces the canonical cylinder. That's one of the remarkable facts about this construction of derived tensor smash product, is that if we take the usual one simplex and we smash it with an object, we get the canonical cylinder. Basically, that happens because the construction of this derived product used these canonical framings, which were constructed using the canonical factorizations. And so if we unwind this definition of the canonical framing, we will see that the smash with delta 1 always produces the first stage of this cosimplicial frame, which coincides with the canonical cylinder. So that's the reasoning behind this formula for the suspension of a space.
So, sorry, we have there is a question in the chat.
Oh, okay. I can't see the chat. Wait just a moment. I will try to. Oh, I'm sorry. Someone who asked the question, can you please retype it, because I have only the old version of the chat. I mean, I just entered the meeting. So.
Can you please remind what is a smash product, derived smash product?
Oh, okay. So. Okay. Well, I'm actually not sure that I want to do that. I'm deeply sorry for that, but basically, if you perform all of the constructions above, which define what is a derived product, but instead of just plain model categories, you will use pointed model categories. So here we will have C times simplicial pointed simplicial sets. Then what we'll get will be the smash product. So the smash product is the result of this construction for pointed simplicial sets and pointed model K-squares. I'm not sure that I want to dive further into an explicit definition. I guess maybe. I'm not sure that I want to do that because perhaps it's possible to define the smash product as a cofiber of a certain map from as a cofiber of a certain map, but I guess we will need to do some replacements, and I'm not sure that I'm ready to define it right now. I'm sorry. I don't know, maybe there is a simple way to do that, and I'm just saying all these fancy words. Okay. Oh, I guess. I guess that's the easiest way to say this. So we just so we just performed this construction for pointed simplicial sets. Maybe another way to sort of better understand what is happening is that we have the following formula for just the plain smash product between a cosimplicial object and the simplicial set is that if we apply the functor which adds a disjoint base point to the simplicial set, then the smash of this simplicial set with this cosimplicial object will be just the usual tensor product with this simplicial set. And so yes, one can sort of understand how to construct this thing using this adjunction which we have between model K-squares and pointed model K-squares, where in one case we just add a disjoint base point, and in the other we forget about the base point. Okay, so let's move on to a familiar result about suspensions and loop functors. So for an arbitrary pointed model category, for arbitrary cofibrant object X and fibrant object Z, we have a sequence of isomorphisms. So if we take homotopy groups of this mapping space between X and Z, so that's, I forgot to mention this, but this is usually called the function complex. For some reason, I referred to it as internal hom. It was completely baseless. Of course, it's a function complex. So it's basically a homotopy type of a space of maps between X and Z. Okay, so if we have, if we take homotopy groups of this space of maps, and then it's, well, this part is, I guess, quite clear, but it will be explained in the proof in just a moment. So we have an isomorphism with homotopy groups of the right function complex or right mapping space, and then we have an isomorphism with the set of maps from.
Sorry, here now we in the enriched case.
No, I mean, for arbitrary model category, we can construct this functional complex as was described earlier using these adjunctions.
Okay.
And this thing here belongs to the homotopy category of, strictly speaking, it belongs just to the category of simplicial sets and even pointed simplicial sets, because here we consider the mapping space of maps which preserve the base point. So we have the canonical base point, which corresponds to the map which collapses everything to the base point. And so, yeah, and we have an isomorphism. So these are in general just sets. And so we have canonical isomorphisms of such sets. And this is a set of homotopy classes of maps from suspension applied T times to X into Z. And from homotopy classes from X to T-fold loop space of Z. So how do we prove this? Well, we just use the associativity of the smash product, meaning that we can take the product many times, and in the end, it is the same as taking the smash product inside of simplicial sets on one side, and this gives us ST. And the rest is just an application of tensor homojunction, basically. So we replace the suspension with this smash product. Then we use tensor homojunction to replace this set with this set. And then we just see by definition that this is PT of the derived mapping space. And then we recall that since X and Z are, so this is cofibrant and this is fibrant, we actually can replace the derived mapping space by just mapping space. So, and this gives us the sequence of isomorphisms. Okay, so that's a quite familiar lemma, and yes, from homotopy theory, most people know that, well, the suspension shifts homotopy groups and stuff like that. So the interesting thing is that this holds in great generality. So in fact, this is just the property of pointed model categories. Doesn't matter if we have topological spaces or chain complexes or whatever. Okay, so another familiar from topology thing is that suspensions form homotopy cogroups or co-H spaces, as they're classically called, and loop spaces are homotopy groups or H spaces. Well, first of all, a small short recollection of what is a cogroup object in an arbitrary category, and basically that just means that if we have an object, then it is a cogroup object if the functor which is represented by X lifts to the functor a functor into the category of groups. And similarly, a group object is such an object that the functor which is co-represented by X lifts into a functor. I'm deeply sorry. I think we should have this. Lifts into a functor into groups, to a functor into groups. Okay, so that's good and well. But as it turns out, in point of model category, no surprise, suspension lifts into a functor into co-group objects, and the loop space functor lifts to a functor into group objects in the homotopy category. And the proof is just an application of the result about the homotopy category of spaces, because as we know, these home sets are calculated using homotopy groups. And about homotopy groups, we know that they're groups starting from dimension 1 and the abelian groups starting from dimension 2. So obviously we have this result, and moreover, we can say that if we apply twofold suspension, then it lifts into a functor into abelian group objects inside of the homotopy category, and similarly for suspension. So no surprises here again. Now, another sort of familiar thing from topology is the fact that we have a coaction or action on co-fiber or fiber of suspension or the loop space. So in one case, it's the suspension of the source of a cofibration, and in the other, it is the action of a loop space of a target of a fibration. So to see that we actually have such a coaction, it is enough to construct a right action. Right now, it looks more like a left action, but I hope that this letter R will convince everybody that that's the right action. So we want to construct a right action of such a group on such a set of maps. Well, I'm not sure that it's intelligible here, but the idea is that we just take a representative of a map from the suspension to the space under some mild assumptions. So I guess these mild assumptions are precisely the ones that we made here. That here we have a cofibration and the source and target are cofibrant. So we can pass from left homotopy to the right homotopy to a right homotopy, and so a representative of a map from suspension to a space is the same as a map from the space to the path fibration of the target. And so we have a cofibration here. We have a trivial fibration here. So that means that we actually have a lift denoted by alpha. Once again, I am sorry if it's not intelligible, but here we have a lift. And since we have this condition, it means that there exists such a W from C to X, such that WG is equal to P1 alpha, and then we define the action of of H, because we should have a right action. So an action of H on U by taking the class of this map W. So let's consider an example of this construction. I will be a bit hand wavy, and instead of providing a real example, I will provide a dual example. So let's consider a fibration and assume that our space X is just S0, so 2 points. Then the action we define before, well, the dual action. So here we define coaction, and here we should use the action of the loop space. So the action that we have is actually the action of pi1 of the base, which is the map, the homotopy classes of maps from the suspension of S0, so from S1 to B. Oh, of course, I forgot to mention that we work now in the category of topological spaces or pointed simplicial sets. Yeah. So this is an action of pi1 of B on pi0 of F. And once again, from homotopy theory, we probably know how this action works. So assume that we have a loop H in the base, then we can lift it to a loop in the total space, which starts from a fixed element on which we act and ends in another element, which is the result of this action. So that's once again, we arrive at something very familiar from standard topology. Although we use all these fancy words about pointed model categories, actually the origins of all of it are pretty standard and pretty well known. Well, I guess all this material is well known, but I mean that it's not related to model category theory. Okay. So this construction actually is quite factorial, although on the way we made a lot of choices, it turns out that in fact it didn't really matter. And if we have a cofibration with cofiber C prime and another cofibration with cofiber C, and we have a morphism Q1 and Q2, which make this square commute, then we have an induced map Q3 from C prime to C, which, as it turns out, is sigma Q1 equivariant. So this map is compatible with coaction of sigma A prime on C prime and coaction of sigma A on C. And of course, we have the dual statement, meaning that if we have a fibration with some fiber and we have another fibration and we have a map, then the induced map of fibers also commutes with, well, with the section. So now we're ready to define cofiber sequences, which are precisely these kinds of triangles I was talking about earlier. So what is a cofiber sequence? Well, first of all, consider this three-term diagram inside of our model category C. Of course, it's pointed still. And assume that we have a right coaction of sigma x on Z. So it's very important to remember that all this business about fiber or cofiber sequences doesn't really work if we don't include the data about the action or coaction, because we can't just say that some two maps form a cofiber sequence. We need to have this additional structure which shows that, well, which exhibits one of the objects as a cofiber or fiber of another map. So we say that such a diagram where we have this coaction is a cofiber sequence if it is isomorphic in the homotopy category to sort of standard diagram where we have a cofibration, its cofiber, and the standard action of the suspension of this X tilde, which we defined earlier. And the dual definition gives us fiber sequences. So we have these two kinds of sequences, which do not look like sequences right now, but we'll see in a short while that we actually can extend them infinitely in both their directions. Okay, But before that, let's discuss another absolutely classical construction from homotopy theory, that is our boundary map. So we, of course, know the construction of a long exact sequence of fibration or long exact sequence of co-fibration, which is usually called long exact sequence of a pair. And this all actually comes from the notion of these fiber and co-fiber sequences in homotopy categories. So in fact, we have this map from Z to sigma x, which is defined like this. So we start from Z, we apply the coaction morphism, we get this space. Since it was a coaction, it's precisely what we need. And then we just collapse Z and map sigma x into sigma x identity. And we get the connecting homomorphism, sort of. It's actually not homomorphism. It actually has a geometric meaning. So it comes from the homotopy category. And this boundary map is defined like this. And of course, we have the dual construction for fiber sequences. There we will have an action and a loop space of the base. Okay. So that's another important thing about fiber and fiber sequences. So this means that we actually can extend a co-fiber sequence by this connecting homomorphism, and then we can apply the functor sigma and get another 3 terms, and then extend again, and so on. So we actually get an infinite sequence. Yeah.
Why the target of the arrow in the boundary map is a Z cap sigma x?
This one.
Yeah.
That's just because that's a coaction. So what is a coaction? First of all, what is an action? So assume that we have a group and we have some object, then an action is a morphism like this. What is the dual notion of an action? It's a coaction.
Oh, okay. Thank you.
Yeah, I mean, it's always confusing to think about dual objects because we're so used to actions, and coaction is something unexpected, but actually it's very natural. Yeah, so we have this boundary map, which is defined on the homotopy category, and not just on homotopy groups, as some courses in algebraic topology may make you think. But let's move on. So now let's discuss pre-triangulated categories. So first of all, we start from a module over the homotopy category of pointed spaces. And we assume that it is non-trivial, non-empty. Then a pre-triangulated structure on this S is, it is two classes of sequences. So fiber sequences, well, it's just a name. Right now we think abstractly. So we have just some module over the homotopy category of pointed spaces. We don't know if it came from model category or if it didn't. We just think of distinguished subsets of 3-term diagrams. So we call them co-fiber sequences and fiber sequences. And we say that they should satisfy the following axioms. So first of all, co-fiber sequence is a diagram consisting of 3 terms. As I said before, we should have a coaction of sigma x on Z. Maybe it's not quite clear, but if we have this closed structure of a closed module over a homotopy category of pointed sets, then we still can define what is sigma x, because we still have this structure map of product over this category. So it's still just a smash with S1, and similarly, omega is defined as a home from S1 to X. Additionally, cofiber sequences and fiber sequences should be replete, meaning that if we have an isomorphism of sequences, and isomorphism of sequences and is an isomorphism on objects, which is equivariant with respect to action or coaction on one of the objects, and which makes sense. So if we have such an isomorphism of sequences, and one of the sequences is a cofiber sequence or fiber sequence, then the other one is too. So that basically means that cofiber sequences form a replete subcategory of all possible sequences. And by sequence, I mean a three-term diagram, I guess, to make everything better with action or coaction. Additionally, the sort of identity triangles belong to cofiber sequences and fiber sequences. So a triangle of this form is a cofiber sequence, and a triangle of this form is a fiber sequence. Okay, the next axiom says that if we have an arbitrary morphism in our category, which is for some reason denoted S, but C, but it should be S. Then there exists a fiber sequence which includes this map, and there exists a cofiber sequence which includes this map. Also, a thing familiar from topology, we can always replace a map by a homotopy equivalent map, which is either a cofibration or fibration, and then we can take corresponding fiber or cofiber sequence, and we will get this result. Next thing, the functor sigma preserves cofiber sequences. So that's the thing I was talking about. So we can shift the cofiber sequence to the left infinitely many times, and we will still get a cofiber sequence. And similarly for the functor of a loop space, so we will get a fiber sequence. Another thing, there should always exist a filling map. So if we have a map of, well, if we have a commutative square like this, and these sequences are both cofiber, then there should exist this map from Z to Z prime, and dually for fiber sequences. Okay. I have to note that it is somewhat different from what we had earlier, because earlier we had a cofibration and a cofibration, and there such a map existed by universal property, because this was a cofiber and this was also a cofiber, so a colimit. And by universal property of colimit, such map always exists. But in general, we just have two distinguished triangles, and we want to find such a map. And the axiom is that it can always be done. So another important part is Verdier's octahedral axiom, which states that if we have, I forgot from what we should start. So if we have a sequence like this, and right now by sequence I just mean a three-term diagram like this, then we should have four additional sequences. In this case, they should be cofiber sequences, and of course we should have the dual statement. But basically, we should have 4 additional cofiber sequences which all fit together into this octahedron, and that basically sort of allows to define a composition between yeah, it allows to define a composition between maps and sequences, something like that. Okay. So that's Radius axiom. Another axiom is this axiom which relates fiber and cofiber sequences. So assume that on top we have a cofiber sequence, and on the bottom we have a fiber sequence, and assume that we have this solid arrow diagram. Then this map from Z to Y prime should exist. And additionally, we require that this map here, alpha tilde -1, it should be the inverse of the adjoint map to the map alpha, which belongs to this group. So X to omega Z prime is necessarily a group. We can apply the adjunction, so we get sigma X Z prime. And here we have the adjoint morphism alpha tilde. And then we want to take alpha tilde inverse. And if we define this solid diagram like this, then there should always be a filler. And of course, we have a dual statement, so we flip everything. Okay, final axiom of pre-triangulated structure. So the product should preserve cofiber sequences in each variable, and this thing should preserve fiber sequences in second variable, and cofiber sequences should be transformed into fiber sequences in the first variable. So that's basically the list of all axioms. And we say that S with pre-triangulated structure and all small coproducts is a pre-triangulated category. Sorry, not just products and coproducts. So it's a we call it a pre-triangulated category. And in pre-triangulated categories, we have the following, actually very abstract property, which states that if we have a cofiber sequence and we have an arbitrary object of S, then we have a long exact sequence of sets of homotopy classes, which actually, starting from here, are groups. And after here, we have an exact sequence of sets where exactness, for example, in this term is considered in terms of action of this thing on this thing. So that's an analog of long exact sequence of whatever you want to call it, fibration, cofibration. I guess here it's cofibration, so long exact sequence of cofibration. And another result, which also follows just from axioms of pre-triangulated category, yeah.
What exact sequence of sets means?
Oh, yeah. Okay. Let me write this down. So, in one term, it means the following. So, G upper star A coincides with G upper star B. if and only if there exists an X in this group sigma XW, so here, such that they are connected by an action of the sets. So they lie in the same orbit. So that's exactness. That's exactness, yes. Well, partially exactness in this term. And another condition is that d up star c is equal to d up star d if and only if they also lie in the same orbit, but this time with respect to the action of the previous group. So there exists an element of this group such that we have this. So this this map here is still a homomorphism of groups, although the image of this homomorphism may not be normal. So when we take a quotient, it's just a set. So, but still, we can formulate such a condition, and we will get this sort of exactness. But I guess you should be familiar with that because, when you describe this exact sequence related to homological spheres, there was some similar condition. Yeah, similar condition of exactness at the level of sets. So we had a group which mapped into a set. And you said that a map between sets is exact in this term if like objects with the same elements with the same image are in the same orbit. Yeah. Okay. So another thing is that if we have a morphism of cofiber sequences, meaning that this third term commutes, well, is equivalent with respect to the coaction, then if two of the morphisms A and B, first two, are isomorphisms, then C is also an isomorphism. And that's once again just an abstract property of pre-triangulated categories. So we don't need any data that came from somewhere, example from model category. That's just an abstract result about pre-triangulated categories. Okay. Finally, the notion of a morphism between pre-triangulated category, which somewhat mimics the notion of a Quillen adjunction, or maybe for someone more algebraically inclined, that's just some very natural thing. But we have these exact adjunctions between pre-triangulated category. And an exact adjunction is an adjunction of modules over this homotopy category of pointed spaces, such that, well, we have this adjunction isomorphism, this isomorphism, which shows that it behaves well with respect to this module structure. But most importantly, we should have this condition that F preserves cofiber sequences and U preserves fiber sequences. And this condition somewhat exhibits a deficiency of the notion of pre-triangulated category because we can't drop any of these two. So, for example, for Quillen adjunctions, we can assume that only the left functor is left Quillen functor, left adjoint. And then we can deduce that the right adjoint is also a right Quillen functor. But here we have to assume that both F and U preserve fiber sequences. sorry, both. So F preserves cofiber sequences, U preserves fiber sequences. Actually, I'm not sure that that's a deficiency. Maybe this result still holds if we drop this condition, but I'm basing my talk on the Hoyle's book, and he says that he doesn't know if it's true. Maybe it's true. Maybe I don't know. Maybe someone can prove this result. It would be very nice. Okay, so we have this notion of exact adjunction, and then we arrive at the second kind of structure on the homotopy category, this time of a pointed model category. So the theorem states that the homotopy category of model category is pre-triangulated. First of all, if we have equivalent adjunction between pointed model categories, then its total derived adjunction defines an exact adjunction between homotopy categories. So it means that left adjoints preserve cofiber sequences, right adjoints preserve fiber sequences. Right equivalent functors, left equivalent functors. That also means that we have a homotopy pseudo-2 functor from this category of pointed model categories with morphisms given by equivalent adjunctions, and pre-triangulated categories and exact adjunctions. Okay, so we're almost finished. I wanted just to make some final remarks about triangulated categories and stable model categories. So assume that we have a pre-triangulated category. We say that it is triangulated if the functor of suspension is an equivalence. And we have the following observations. So since the functor of suspension is an equivalence, the functor of the loop space is also an equivalence. And they are mutually inverse equivalences. So we have the following properties of triangulated categories. So first of all, any triangulated category is additive. Secondly, cofiber sequences coincide with fiber sequences, and we call them just triangles. And adjunction between triangulated categories is exact if and only if only one half of it is exact. So in the case of triangulated categories, we can drop the assumption that, for example, U preserves fiber sequences. It is enough to assume that only F preserves cofiber sequences. Okay, so that's all very nice. But I have to point out that the name triangulated category here is somewhat misleading because it's not a triangulated category from algebra. It's a triangulated category in the sense that we have all these axioms, and also it is a module over the homotopy category of pointed spaces. But maybe there are some classical triangulated categories which are not of this form. So let's discuss it a bit more. So what is a classical triangulated category? So first of all, it should be additive. We should have an additive functor sigma from the category to itself, and which is I guess an equivalence. Maybe we can deduce that. And I'm sorry, I'm not. I have to confess, I'm not very proficient with triangulated categories, so maybe I'm missing something. So no, yeah, it should be an equivalence, right? Otherwise, it would be strange. Okay, so and we should have a collection of distinguished triangles which look like this. So this correction should be replete. This kind of triangle should be, so this should be a triangle. If we have a morphism, then it fits into a triangle. Sigma preserves triangles. So if we apply sigma to a triangle like this, we get a triangle. We have a fill-in like this. So if we have a triangle here, right now, so now it doesn't matter if we have a fiber sequences, they're the same. We should have a Verdiès axiom, which is basically the same as before. And that's basically it. And the result states that each triangulated category in the previous sense is the classical triangulated category. Okay, so we're almost over. I want to conclude this talk with the following short observation. So first of all, we call a model category stable if suspension is an equivalence on the homotopy category. And clearly, if model category is stable, then its homotopy category is triangulated, just by definition. We have this result that each triangulated category is a classical triangulated category. And finally, we have, I guess, these three examples to illustrate what's going on. So in category of spectra, with well, in the usual model structure, the functor of suspension is an equivalence, which means that it is a stable model category. Or in the category of chain complexes, everything is even simpler because suspension or shift is in equivalence even at the level of the category itself. So category of chain complexes is also clearly stable. Finally, I guess I wanted to say something about some simplicial version of chain complexes. So here we should consider, I guess, modules over spectra. So if we consider modules over spectra, then dot-Kahn correspondence gives us stable dot-Kahn correspondence gives us another example. So modules over spectra is also a stable model category. Okay, I guess that's it for today. If there are any questions, please ask them now, or not ask them. You can ask me later. Okay. Okay, let me stop the recording.